Okay, thank you very much, everyone, and thanks a lot, Rama, for inviting me here. I'm a little bit sorry because I'm not really an expert on systemic risk, and I hope you can get something out of my presentation. It will be more into some statistical idea and some related concepts that are behind systemic risk. And essentially I will talk a lot on conditional distribution or conditional quantiles and the importance of tail dependence. And you'll see that it comes naturally in the context of systemic risk, but I don't have really an empirical evidence and a lot of experience with data. But I did enjoy a lot this week, and I learned a lot by listening to the other talks. So this is a joint work with Professor Claudia Chado, who's at the Technische Universität München. I was there last year during my sabbatical through the Alexander von Humboldt Foundation, who funded it, but originally I come from the University of Waterloo. So here's more or less the outline. I've been inspired by the first time I worked on that was actually after reading the paper by Adrian and Bruno Meyer on COVA, which was based directly on estimating having a systemic risk measure that is linked directly to a conditional quantile. And so I started to work on conditional quantile, on quantile regression, and trying to understand how to estimate them. And I had a hard time because I didn't find it easy, and especially I had a hard time understanding how quantile regression could work and what are the limitations of quantile regression. So throughout the study, we kind of come up with a way to visualize conditional quantiles, and I'll present this essentially by changing the margins, doing a transformation on your data to better observe tail dependence and better observe conditional quantiles. And when you understand how to visualize these conditional quantiles and you see how they look like, then you realize that quantile regression may not be totally appropriate because it has very strong assumption. Either you fit a linear quantile regression or nonlinear quantile regression, but there are very strong assumptions behind. And it seems that you cannot really capture easily, at least, any time you have tail dependence or asymmetry in your data. So we were thinking about other approaches, and I will hint about that. We have very limited work. It's still work in progress and current work, so I don't have a lot there. And I'll conclude that, in fact, I don't believe in quantile at very high level, so because it's always very hard to estimate a quantile at very high level, and when you go to conditional quantile, it's actually even harder. So is more or less the setting. It's a little bit abstract, or you can put behind this setting more or less every of your favorite data or variables. I'm going to consider two variables, x and y. You can think of them as the assets of one company X and the assets of another company Y. You can think of it as the aggregate loss of the system, like Y being the full system and X being a big bank. And when you take two such random variables, their interaction can be of many types. And very often, if you think, for instance, about a big bank and a small bank, it's very clear that if they do business together, if one defaults, it will have some effect. If it's the big bank defaulting, it will most likely have a very strong effect on the small bank. But if the small bank defaults, it doesn't have the same effect on the big bank. So very often, it doesn't, the dependence should not be symmetric. Dependence, the effect of one bank on the other should not be the same as the other bank on the big bank on the small bank, and vice versa. So we were trying to understand how to model dependence in a non-symmetric way, x given y being different from y given x. So when I write this, I mean x conditionally on what happens on the variable y. And especially when, in the context of systemic risk, we are always interested in extremes. Thinking about the COVA risk measure, in context of systemic risk, for instance, X would be a financial institution, Y could be a financial system, and saying that X or Y is extreme could be seen as X and Y goes beyond the value at risk level. So you observe a loss on the financial institution that is an exceptional loss, an exception for the its value at risk. It's like bigger than 99% of the time, for instance. So understanding this dependence, X given Y, what happens on X, on the distribution of X when Y has some extremes, or what happens on the distribution of Y when X has some extremes, is definitely useful in the context of systemic risk. This week we also had an example with the presentation of Raphaël Douadi, where it could be useful in the context of stress testing, where you have scenarios and you want to understand what is the distribution of X, for instance, conditionally on one scenario. So if you say that Y can be the aggregate loss of the company, X a particular factor, and then you're conditioning on this factor being at some level, and you want to understand this distribution of Y given X. So what happens in this particular scenario? In particular, X can be multidimensional. It will actually not be a big problem. So to understand this joint distribution, what a lot of people do is they try to model the joint distribution, and very often it ends up being a bivariate normal distribution, because this is a very common multivariate distribution. Now, what I want to do is trying to understand a conditional distribution from another angle, and for that I'm going to decompose a joint distribution between marginals and copulas. I guess a lot of people are familiar, but I'm just putting this back in case you don't know this decomposition, where a joint distribution can always be decomposed into marginal distribution and then a copula that link them together. And this decomposition is unique if you have a continuous distribution. So I'm going to assume that the loss can take any values, aggregate assets can take any values, so I don't have problems with unicity. And one particular property, and I'm going to work on a lot on this property, is that if your observation, if you scale them by any increasing transformation, even non-linear, you take the log, you take the exponential, you take a power, as long as it's increasing, it has no effect on the dependence function, on the copula. I'm not saying it has no effect on the conditional distribution, and it has effect on the conditional distribution, but it has no effect on the dependence. So effectively, the copula between two variables will be invariant, even if you change the scale or if you look at a different scale for your data. One change that we do very often is you start from your data X and Y, and they have some distribution. It could be any distribution, and when you apply the distribution function on your data, you can transform them. So fx denotes the marginal distribution of X. You apply it to the data on X, and then you obtain a uniform variable. The same thing here if you apply it on Y. So you start from a data that might be valuing like any assets, maybe on the real line or maybe on the non-negative real line, but at the end you get something that's between 0 and 1. And empirically it's very easy to do this transformation, because the empirical distribution is just the rank. So you take your data, you rank them, and this gives you the empirical distribution. And so this thing is just the rank of the company divided by the number of the rank of the observation divided by the number of observation. And so taking your data set, you can transform them and get the rank out of the number of observation. And once you're there, you have a distribution that's uniform between 0 and 1. And now you have kind of isolated the marginal effect, And you can work with these uniforms that are not anymore linked to the original margins, but the dependence between the variables is the same. So by doing this transformation, I haven't changed the dependence. And it turns out that sometimes, and in particular when you look at interpreting the conditional distribution, it's going to be useful to look at standard normal distribution. So we're going to go from the uniform to push them to a normal scale, which means now I take the uniform and I apply the quantile function, which is the inverse of the distribution of a normal 0, 1. And when you do that, you get new variables that are actually normally distributed n 0, 1. So what I did is, starting with any data set that has any distribution, scale, like applying some increasing function to them, so that I get to a normal 0, 1 scale. And now what I have to study is just x and y, who are both normally distributed 0, 1. And it turns out that to interpret the tail dependence and to even visualize the conditional distribution, this is going to be useful.
I'm so sorry to interrupt.
Yeah.
I don't understand this uniform distribution business. Because if I'm concerned with tail events, and I have an observation of a set of samples, all I know is that the worst case is probably worse than any of the numbers that I've actually seen. But I don't know how much worse. And if I now rescale it so that I'm just ranking them, haven't I implicitly assumed that I've already seen the worst case, when actually the big problem is that we don't know how bad the worst case really is?
I think transformation.
Yes.
But how do you know what transformation to apply?
So any transformation is monotone. I mean, the extreme things will be near 0 or 1.
Okay, if the answer is no, forget it, go on.
Oh.
So if you have like n observation, then you would have this, and they are sorted. Your transformation would just be to put 1 over n here and n over n here.
But how do I know that's a transformation of the underlying probability distribution? Because I might have not observed.
But then I can come back to it.
That's true. Okay. That's true, but that's a sample.
So I'm not losing completely the information on the margin because I transform the data, but I can transform them back. So once I have the uniform to come back to here, I would just apply the quantile function. So you can still come back to the original scale. And we're not losing the original scale, we're just going to focus only on the dependence. And the you will see on the, actually, I have a few examples to try to illustrate how you can see dependence. I'm sorry for those of you who know that very well, because it's actually quite well known for if you're in statistics. So the Gaussian copula is like the bivariate normal is the most common. When you talk about two variables, you calculate the correlation, and you feel like you know the distribution. That means you have in mind that this is a bivariate normal distribution, and that the correlation characterizes the distribution. Now here I write tau. Tau is like the correlation, but it's a measure of dependence, a global measure of dependence, so like the correlation between data, but it doesn't depend on the margins. So it's a measure of dependence between x and y that depends only on the copula. And there are some linked, of course, that when the candle's tau is very large, like goes to 1, it's the same as saying the correlation is maximum. So a candle's tau of 75%, yeah.
Can you tell us the correlation in the transform variables?
We can actually, and I wanted to calculate them, but what I have in mind is that when the candle's tau is 0.5, this corresponds to a correlation of 0.7.
Okay, so it's connected to the correlation.
It's completely connected, and there's a link between the correlation coefficient and the candle's tau. But the good thing with candle's tau is that it doesn't depend on the margins, and so you can compare different dependence, and you're not affected by the fact that they have different margins. So it's
rank correlation.
It's rank correlation. Not exactly.
It's like a rank correlation.
It's like a rank correlation. Like Spearman's law is another example of dependence measure that would depend only on the copula, not on the margins. So this is the dependence that is most used in papers. Like if you take a random paper in finance, very often there's the Gaussian copula behind. And so on this scale, this is the scale 0, 1, 0, 1. So I represented x and y, now scale between 0, 1, and the extremes can be obtained. You can be seen from these two corners. So you can see when x and y are small together, they are going to be here. X and y are big together, they are going to be here. So you can still see these extremes together, but on a different scale. One thing is, so this is the uniform 0, 1 scale, and I said I'm going to transform them to normal 0, 1. And one reason is that it's much easier to interpret the contour plot. So what is a contour plot? These are the graphs that are here. So on the x-axis, this is like a normal 0, 1, normal 0, 1, x and y. And these are the contour plot of the density, of the joint density. So you can think of a map like a mountain, and the density is highest here, and you have ellipses, you observe ellipses. Now from these graphs, there are a few things. First, if you look x and y, if I switch y and x or x and y, I get exactly the same graph. So these two graphs are symmetric. And what I was saying about the fact that the dependence between x and y, and x given y and y given x can be different, and it's very intuitive that effects of a big bank on a small bank is not the same as a small bank on a big bank, then this is completely not there. Because if I switch x and y, I get exactly the same copula, same dependence. It actually means that here, in this context, when you condition, you're working on the distribution of x given y, or on the distribution of y given x, you'll have exactly the same effect. And you cannot capture any asymmetry between the role of the two variables. Another thing that can be observed here, and will be observed more by comparison, is actually you can show that with this copula, and if you're interested, you can actually read the book of Alexander McNeill-Roussier and Paul Embrechts and Rüdiger Frey. They have some good example where they show that in the extreme, the probability to have joint default, if you model the dependence between defaults with a Gaussian copula, is too small to be realistic. And you need to go to other copulas, other dependent structure that capture the fact that you can have joint defaults in the tail. And an example is the student copula, which is on this side. And the student copula looks very similar to the Gaussian copula, but now has some higher probability to have joint tail event. And then in these corners, it's not so visible, but in this corner, there's a higher density of points, and there's a non-zero probability. When you go find the tail, there's a non-zero probability to have joint defaults. When you look at the contours, and the good thing of scaling everything with a standard normal 0-1 scale is that now the contours can be comparable between the different copulas, and this will be very helpful also in what follows. Each time you will see that the contours goes very steep, and not anymore like round or ellipses like this, but more like this. This will be a sign of tail dependence. So on the contour plot already, we can see that there's some tail dependence. Same thing here, the ellipses are kind of transformed, and you can see some tail dependence appearing here and here because they are not anymore ellipses. And the student copula usually already is a better fit when you go to financial data and you look at dependence between financial instruments. Now, more copulas. Now, copulas that are tail dependence but not symmetric. Here, one particular thing is that what happens in the left tail, so when both banks goes down or when both banks goes up, is exactly the same with the Gaussian and student. So each time you work on a student copula or student multivariate dependence, you're also making the assumption that you have the same effect if in the upper tail when both risks go high, or in the lower tail when both risks goes down. There are copulas that are there also that will kind of solve this problem, and can model upper tail dependence or lower tail dependence independently. And this is an example, for example, the Gumbel copula. Again, it's on a 0-1 scale, and you can see tail dependence here and no tail dependence here. And what happens on the graph is here is like very much like an ellipse here, and here you can see tail dependence. So now you have asymmetry, but asymmetry of behavior in the tail. But again, these two dependence, and if you go now more into specific papers who have worked on dependence between financial stocks and things like that, they often get to the Gumbel or the Clayton. And this is fine, and why they get that is very often you can think of different sectors. They are most of the time independent, except if there's a big crisis. And so in the tail, they can become independent. For instance, they are dependent for losses, but for gains, they have, because they are different sectors, they are independent. So you can think that you have tail, very strong tail dependence when things go badly, but when things go well, there's no tail dependence. And so this kind of model is very useful. But one problem, it's still symmetric. So when you look at this x and y, and you flip y and x, you'll see that it's exactly the same graph. You don't see the difference if I flip x and y or y and x on all these things. And so what it means that, again, if you model the interaction between banks using such copulas, it will capture tail dependence and asymmetry in tail dependence, but you will not capture asymmetry in dependence, where the effect of x on y is not the same than the effect of y on x. So we had all this in mind when we started to work on it, and these are two other copulas, so the Frank copula, Joe copula, and there are many others. The Frank is, particularly in the sense, is very flat here on all these things, and it has total absence of tail dependence, and you will see it's independent in the tail, in some sense. And the Joe copula is very strongly dependent. So, back to our topic on COVA, on systemic risk, and we want to estimate or think about a conditional quantile. So what is the effect of this dependence on conditional quantile? How does it affect our, for instance, the COVA? So it's a very simplified version of COVA. There has been many versions of it, and I'm really going to present just a very simple one, not necessarily the one that is exactly like in the paper of Adrian and Bruno Meyer. So you have aggregate assets, for instance, of a financial system, and X being the assets of an individual bank. And you look at the value at risk of the system. So this is the quantile at level Q. It means that it's the capital, the system, or it's the maximum loss the system would have with probability Q. So if you take Q equal to 99%, you can think of it as, in 99% of the case, actually I should put 1%. In 1% of the case, the assets will be below this value at risk. You can also edit the sign depending if you think about it in terms of capital requirement or in terms of quantile. To make it simple, I'm just going to think it's a quantile. And if it's negative, then you just take the opposite to get your capital requirement. The COVA would be so you look at X, and you think X is in a stress situation. So I stress X, and the institution being under stress, one way to see it is that the value of X is at its value at risk level. What it means, I'm in a scenario where X has lost as much as it should have lost, like in 99% of the case. Then what happens on the system, and how much more capital do you need? Like, what is the conditional risk? What is the conditional value at risk? And then the idea that was behind is to say you can look at the systemic risk contribution as how much more capital you need, how much the effect of X has on the system, how much does it increase the capital it needs to hold to avoid default in some sense. So the systemic risk contribution was based on a conditional quantile of one variable given another one being in the tail. And I'm going to write it this way. So this is like a quantile, unconditional quantile, inverse of the CDF, and this is the inverse of the conditional distribution. Now, how to compute this? So the good thing is that there's a formula, and the formula depends on the ingredients of a joint distribution. A joint distribution depends on margins and copula, and you can actually find, by differentiating the copula with respect to one of the variable, you can find a formula for the conditional quantile at some level Q, and it depends on the marginal of X, the margin of Y, and the copula. And so, given that we had this, and then we said, okay, what if we take marginal distribution being normal 0, 1, and then look at how they look like. And so I want to make you understand how to visualize these conditional quantiles. So I'm starting with quantiles of a normal 0, 1. So you have the normal 0, 1 density, and we're going to look at 5 quantiles. One is 99% quantile, 90% quantile, 50%, 10%, 1%. And so you have these 5 numbers. If you know these 5 numbers, you can kind of plot the distribution. And now I want to know, so this is the unconditional distribution of the financial system after normalization. We have all normal 0, 1. Now what happens if I have a big shock in the market and X change? Now, if X is independent of the system, this is how we're going to read the conditional quantile. On this axis, I put X. X is my shock, or my other bank, and depending on the value of X, I'm going to plot the conditional quantile as a function of X. And so for each X, I compute 5 numbers that exactly corresponds to these 5 numbers. Now, if X and Y are independent, what happens on the conditional distribution? It just doesn't change the distribution. So these numbers here, minus 2.23, is exactly the number that we have here. So whatever X is, the conditional quantile at 1% doesn't change. So we get this horizontal line, and this is a sign that actually X has no effect on Y or on the conditional distribution of Y. So anytime we're going to observe that conditional quantiles are horizontal, it actually means that X has no effect. And you can visualize how the distribution will change as a function of X by thinking of, for each X, you have 5 points, and you can think of the density of a normal around these 5 points exactly like this. And if these 5 points goes closer, then it just means that the normal distribution will become like less volatile, and if these numbers become wider, it becomes that more volatile. So if you have a Gaussian dependence, what happens is the conditional quantiles are linear. So this is also well known, but I find it, to understand the rest, you kind of need to get this very clear. The reason is like, if you take X and Y a bivariate normal, let's say with correlation 71%, then you can also write X and Y as a decomposition that Y writes as rho X plus epsilon, where epsilon is independent, and rho is the correlation. And then when you calculate the conditional quantile, it's actually the same thing, rho X plus the quantiles of epsilon. And so what happens to the distribution now? What we see is that when X increases, the middle quantile in the middle, which is the quantile at 50% of a normal distribution, kind of shows the mean. The mean is going up with X. That's well known. The conditional mean, when you have a Gaussian risk, is just linear in the conditioning variable. Now, how about the variance of the distribution? When you look at the conditional variance as a function of X, what we see is that the spread between these lines stay constant over time. So the conditional variance for each x, when you condition, the spread here is exactly the same as the spread here. So the distribution hasn't changed spread, doesn't change volatility. The only thing is that these numbers, these numbers were like a little bit closer. And the reason is that the correlation is positive and close to 1. If you increase correlation, what happens? The slope are now increasing because the slope of all these lines is exactly 0.71, the correlation. And these slopes go together. And at the limit, if the correlation is 1, then the conditional quantile of y given x is just x because they happen exactly. You can predict y as a function of x. So at the limit, all these lines just goes together and to the black line, which is y equal x. And so that's what we see on the Gaussian coupler. Yes?
Small technical question. This condition that you always use, is it x equal to x or less or equal to x?
Equal to x. So I condition on
To x?
always equality. So it's x equal to x.
It's equal to the value at risk?
Yeah, in the original definition it's actually equal, where I think it should be beyond the value at risk. But
Because if you do that, then there's not necessarily, you don't have necessarily the monotonicity independence. There's a paper by Eric which shows that there is a problem. Even if you take elliptic
Less-
distributions, you increase the dependence coefficients, covar may not increase.
exactly. So covar is not monotonic. There's a problem with that and with this equality. But
I think they changed that.
in
In the second version, they changed.
by looking at the median, I think, instead.
Yeah, they have a subsequent version of the
Exactly. But what I was focusing on is looking at the conditional quantile. And indeed, so here this is the covar where you had equality with the value at risk. And what we find is that there are many problems. One of them is the non-monotonicity that we'll see on the graph. But another problem that I find it very clear when you look at this formula is when you make it equal to the value at risk, then in this formula, the distribution of x disappears. And then it's very clear that when you look at the distribution, you're looking at systemic risk index or measure, and the distribution of what you condition on completely disappears. So the volatility of what you condition on has absolutely no effect on this quantity. And the size also doesn't matter. So there are a lot of things that disappear. Any characteristic of the distribution of x completely disappear from this indicator. And it's totally driven by the copula, the distribution between system and the quantity, and the distribution of the system. But it's not anymore driven by the thing that you're conditioning on. So the bank that goes default, if it's a small bank or if it's a big bank, if it's a volatile bank or if it's small, less volatile bank, the contribution will be exactly the same, as it depends on the distribution of the system and on the dependence only. So that's kind of a limitation. And and also that this conditional quantile can be smaller or larger than the unconditional quantile, and so there are some problems in terms of monotonicity. But anyway, even though it has some problem, the fact to study the conditional distribution, even though if it's maybe not at the value at risk level, what I think is that studying the conditional distribution at the value at risk level may not be the best thing, but studying the conditional distribution at what happens when x moves and x goes to the tail, that can be of interest. So I'm not going to concentrate on this covar, but all these other risk measures actually have the same kind of common theme, is that you can look at this systemic expected shortfall. They have distress insurance premium, which is more or less an expected shortfall, but under the risk threshold expectation. The S risk that we will talk this afternoon. One of the common themes is that you're looking at the magnitude of losses conditionally on being under stress. So you have this question of conditional quantiles or conditional distribution if you don't want to talk about conditional quantile. So tail dependence, I mentioned briefly at the beginning with these examples that you have tail dependence, and what exists on tail dependence is basically looking at the dependence structure and saying for a given copula we can look at the tail dependence as the probability of having joint event in the tail. The problem of this is again the same problem as I mentioned several times, that x given y and y given x are in general not the same. And when you look at that kind of tail dependence, you're having a symmetric definition and a symmetric kind of assessment of whether a copula is tail dependent or not, or a dependence is tail dependent or not. Or we could think of that a big bank will have tail dependence with a small bank, and a small bank won't have tail dependence on a big bank. So there's this asymmetry that is absolutely not captured here and could be captured when you look at conditional quantiles. So I'm going to show you some pictures of conditional quantile for copulas that are exchangeable, so symmetric, x given y and y given x will be the same, and an example of non-exchangeable copula, which is the town copula. And for visualizing them, I'm assuming that they are standard normal distribution. So here are the graph. The first one, you can recognize it. This is the standard Gaussian copula. And the standard Gaussian copula, when you look, these are the linear one. Now, when you look at the Clayton copula, so Clayton, if I go back just so that you have the picture in mind, the Clayton is very tail dependent here, no tail dependence here. And the Gumball has very tail dependence here, no tail dependence on this side. And when we look at the conditional quantiles, it's actually very clear what happens, especially when you look at the normal scale. And I'll briefly show you what happened when you change the margins. It completely, like the conclusions would be completely different. So what happens with conditional quantiles when you have asymmetry in tail dependence? You see that the conditional quantiles, when there's tail dependence, all goes to the y equal x line. So asymptotically, in this corner, we get this asymptotic to y equal x line, or this slope, which is a slope equal to 1. Whereas when you have the Gauss copula, the slope, when you go very far in the tail, is linked to the correlation and will be less than 1. So another thing, if you're thinking of looking at what happens with the conditional quantile and you want to estimate it, a quick estimate in the tail here is roughly would be equal to x, roughly equal to x, when you go far enough. Here it's roughly equal to rho x, so you have a much smaller estimate when you look at linear dependence in the tail. The Frank copula, and anytime you have independence in the tail, what happens is the slope becomes flat. If you remember my first graph, what happens when when x has no effect on y, the conditional quantiles of y given x are just independent, flat. And so here, what happens in this case, it means with the Clayton copula, when x is very big, x has no effect on the distribution of y. And the same here, like Frank copula, on both sides, it has no effect. Now, student copula shows very strange effect where it's non-monotonic as a function of x and creates some problem that if x increase, some conditional quantile may not increase. So it can give counterintuitive result, whereas this is indeed dependence that can happen in practice. So within this work, we've kind of defined tail dependence now in a non-symmetric way, where we'll say that there's tail dependence in one direction if we observe that kind of thing, and tail independence if at some point it becomes flat and independent of x. So this for me would be a tail independence, which is not directly the same as saying that the tail dependence coefficient is equal to 0. An example of what could be really interesting in the case of systemic risk is the case when x given y and y given x have different effects. So here we see that when x goes down, y is more likely to be up. When x goes up, there's very little here. So the effects of x on y is not the same as on a y on x. And this can be seen from the contour plot when you look at the densities as normal 0, 1. And this will be even clearer when we look at conditional quantiles. And conditional quantiles here are quite interesting to see because this copula, when you do y given x, you see that when x becomes very big, then it becomes like linear with slope 1. So very strong tail dependence here. But if we look at the other case where it's like x given y now, so y is here and I'm looking at x given y, and we see that it could be even like almost independent of x, still some dependence in the tail. So depending where you look and what kind of conditional dependence you're interested, there are copulas and there are possibilities of asymmetry of dependence. And these are completely absent of the literature, and not many people work on this, and they are not well developed yet. Now, if you want to do it with not normal 0-1 margins, so that kind of graphs, I can read it very well with normal 0-1 margins, especially because the benchmark is the linear case, which is the Gaussian copula that everybody knows with bivariate normal. If you start to work on conditional quantiles and estimate them with crude data with other margins, then you get completely different results where it's exactly the same copula as before with Cauchy margins, and you see absolutely nothing. And if you do it with exponential margins, you see absolutely nothing. So there's all these tail dependence, whereas the dependence hasn't changed, but you can't see it from the conditional quantiles anymore. So the nice interpretation that we have on tail dependence appearing as being a slope equal to 1 appears to be very closely linked to use standard normal 0-1 to represent the data and work on conditional margins. Now, people have used quantile regression and won't say much on this, but the idea behind is to say, I'm going to estimate my conditional quantile assuming they are linear in the conditioning variable, just to make it simple. When does it work? Indeed, when conditional quantiles are linear or almost linear. And if you remember the graph I showed you, clearly, most of the time, unless you have Gaussian copula, it's not going to work. So, what I wanted to show, okay. Maybe just a comment because I keep transforming my margins and work on normal 0-1. Now, is it useful and can we come back? Because I say, okay, you study the tail dependence, you study asymmetry, everything with normal 0-1. Then what happens with your real margins? Because what you're interested is not with my normal 0-1 scale, but you're really interested in the real scale and what happens in the distribution on the real scale. And actually, it doesn't matter because you can come back, so you can compute this quantile, which I call normalized conditional quantiles, which are the quantiles for normal 0-1 margins. And from them, you can come back to the true quantiles. So it's no problem at all. It's just a function of this normalized conditional quantile and a very simple function that depends on the margins and on these quantiles that you get on the normal 0-1 scale. So my advice would be to just work on the normal 0-1 scale, look at the conditional distribution because there it's easy to interpret and much easier to see asymmetry, and then go back on the original scale. So when I said linear regression, when you try to estimate them, I don't know if you see much, but here it's the Clayton, and I put behind the true conditional quantile, and what happens when you do your conditional quantile and you approximate it with linear, and I have 5,000 points when I do my estimate, so it's not like I use 100 points and I try to do it. I have 5,000 observations, and when I do it, I just get lines that are not too bad, maybe in the middle. So around the mean, I can predict my conditional quantiles not too bad. Here also, not too bad around the mean, but in the tail, it's completely useless. And so if you use quantile regression and you're interested in what happens in the tail, it gives very poor results. And the assumption, I mean, it gives very poor results unless you are in this case, which is the Gaussian copula, which means no asymmetry and no tail dependence. As soon as you have tail dependence, in the tail is going to go, the conditional quantiles are going to cross, which it should not cross, and the conditional quantiles are not going to capture any independence. So for instance, on this side, if you were to estimate anything with conditional quantiles, you would overestimate a lot because actually we have independence in the tail. We have some characterization, and I won't have time to go into the details, but if you're interested, I can talk later, and it's more a bit technical on characterization of when do we have conditional quantiles that are linear, and there are very few cases. In fact, the only way to make it linear is to be able to construct kind of a factor model where you have even nonlinear factor model, then you will get nonlinear quantiles, but at least you can work with nonlinear quantile regression. And you really need to be in this situation. And so we even have a characterization, which is when you take normal distribution, the only way to have conditional quantiles linear is to get the Gaussian copula. If you see linear quantiles, you are in the Gaussian world bivariate normal distribution, otherwise it cannot be linear. So it's not possible to be linear. One question we had is, can we find a way to transform your margins so that the conditional quantiles become linear and we can apply quantile regression? This would be really nice. And I thought at the beginning it would be true, but what we found is very partial answer. If you give me your margin, I can give you a copula such that it's linear. But it's actually totally useless because it's not going to be the dependence you observe. And
when you say it's not linear, you also mean that if I don't know this and I do just the quantile regression, I can get the wrong coefficient for tail dependence, or even maybe
you get completely wrong as soon as there's tail dependence.
Zero even. I can get zero although there is tail dependence.
Yeah, exactly. So you'll be most likely completely wrong. And so what we would want is a transformation to make sure conditional quantiles are linear. But what we found is that yes, you can do it for Cauchy margins. This is the copula actually that makes Cauchy margins linear. And it looks, why not? This is a copula that could be possible in the sense that you have a lot of independence in the middle, normal times, and a lot of dependence in the tails. But when you look at normal 0-1 margins, you see that it's totally different. It's not linear at all. So illustrating again that the scale that you're using would completely change your eyes. And my advice would be work on normal 0-1 margins, then you can see what happens and what is the effect. This is another example of actually copulas where y given x is very different from x given y, as can be seen from the conditional quantiles. So last we have that the Clayton copula, which is very popular and has some tail dependence. It's actually impossible to find any distribution on the real line that would have this copula and with conditional quantiles that are linear. Because if we could find such distribution, we could think we're going to transform to this distribution and not work with this n01, but work with other margins, and then we'll get the Clayton copula, but we can't get that. So there's none of them, and I haven't solved it properly yet in the general case where if there's tail dependence, if we can say something, whether there exists some kind of copula where quantile regression would work. Yeah, I need to stop soon. So it's not directly my work. I'm currently working on it, but I just want to mention. So if you don't use quantile regression, what to do then to estimate conditional quantiles? And there's recent work with Claudia Chado in the last 3-4 years. She has developed a lot of very robust, flexible model, which is called Vines, and allows to, for instance, capture a multivariate distribution and calculate a conditional or simulate from a conditional distribution, and then you can estimate the conditional quantiles by simulation. It turns out to be much more robust and to capture all kind of tail dependence and asymmetry. So she has done a study with stocks of the Euro stocks, and there's a construction. The vines is a multivariate model for dependence, and the construction is you need to find a tree. And I wanted to show you the picture. Actually, the picture is here because it looks like a network, but it's the way it works is you take all your data set and you're looking at a tree that maximizes pairwise dependence. So you look at each one of them. This is the index, this is B and P, and you look at the link between them. And this link is here. This tree is the tree that maximizes the sum of the pairwise dependence. And without having any loops, and then you can identify this tree and construct a regular vine on this. So you maximize this, you find the tree, and this tree is completely based on data. It comes from the data. You're not having any idea on how to, like, what is the link behind that. And then you can fit bivariate copulas for each pairs. So there's no symmetry. You can have asymmetry between different pairs. It will depend on the relationship. And then you can condition and compute the full multivariate distribution. And they have a lot of illustration to show it's much better than what exists. And I think if you really want to have accurate conditional distribution and you want to do it from data in a non-factor model, then this is kind of called a copula factor model, and this I would recommend. So as a conclusion, quantile regression is not always the most appropriate tool, and you may transform, and I hope I convinced you that with the normal scale you can see things that you can't see on other scales, and especially you can observe tail dependence, you can observe asymmetry. And if you want more information on this last thing, which is regular vines and their applications, there are several papers of Clouded Shadow. One recent one on CDS data, where they have done a regular vine fit on CDS data, and I might be working on more on that to see the link with systemic risk. And finally, I just want to point out, because Ludger is here and is a specialist on this, that we're estimating systemic risk at least very often we are talking about valued risk at very high level of confidence level, and this is prone to very high model risk. So if you're unsure about the dependence, you can have a very wide range for your valued risk, and this is definitely a concern. Okay, thank you very much.
Thank you. Questions?
Organ. So you were very nice not pointing out how many people have done these conditional quantile regressions in the literature and saying that's probably wrong. In the
no, it's a popular approach, I would say.
Yeah, it's very popular.
Very popular, because it's very simple. It's extremely simple.
Yeah.
And you have a black box, you enter your data, you say what level you want, it gives you a number, and a lot of people like that.
So my question is, so this is, I don't really I'm not deeply into this literature, but I do recall maybe a year ago or something seeing a lecture where Peter Phillips was presenting on some of these things, and he had a result, and you may know this literature or not, that asymptotically with probability 1 you would get this crossing property happening in very general settings. It's a little bit like what you pointed out as well. So he was also basically saying that these things are very non-robust and would not work. Do you have a sense of where it may fit into the econometrics literature as well to help us kind of connect all these things?
I don't know exactly, but you can see it from the graph that the conditional quantiles at level 70% and 80%, 90% must be ordered. But because you fit each line kind of independently, if you start from data, at some point they will cross, and you can see a crossing here, and the others are not perfectly like
You have
parallel.
a way of formalizing that with probability 1, it essentially would happen.
Yeah,
under
I think
certain
so.
Standard assumptions.
Unless you start from a model that's perfectly Gaussian and you're not starting from data, and you constrain your model to give you. There's a recent paper actually, I think in Econometrica, where they do quantile regression, where they constrain the quantile when you estimate it to be parallel. So there's some people who like working on, if you constrain and you put it as a constraint, then you're going to get parallel. So now instead of trying to capture the tail dependence here, you're just going to have parallel lines. So it means fitting with a Gaussian copula, any copula. So that's what you're doing actually, because here you're just estimating the correlation of a Gaussian copula.
So what
So-
you're saying is you lose the problem that
Yeah,
you might be interested
exactly.
in. and-
You completely lose it. If you can push it to be like not to cross, but then you lose completely the information. Because at least here, one part of the information is that these slopes are actually going to cross, which indicates tail dependence on this side. And the same here. No, I don't have the gumball. But this kind of indicates that there is tail dependence. And if you force them not to cross, then you lose even that indicator. But then at least you have the property that they never cross. But
It just seems to be a very important problem, and it's good that there are different contributions being made that makes us aware. It's great.
So I looked at this issue of tail dependence and copula in the context of CDS data. You mentioned the application. That's a very interesting data set, because if you look at CDS spreads of all names, for example, in the CDX or iTrax index, typically these single name CDS, they have large moves, large jumps, a lot of dependencies in those co-jumps, and so we developed with Marco Avellaneda a model for a CDS portfolio risk, which contains a lot of these tail-dependent features. And what we noticed is that even if you look at expected shortfall or value at risk of the portfolio at pretty high levels, I mean, high realistic is still applicable, like 99.5, it didn't matter so much the type of copula you used, because when we switched from student 4 to student 1 or Gaussian, or we looked a lot of possibilities. It turned out that the actual risk of the portfolio, the things which were generating portfolio risk, were actually not so much in the extreme tails. They were pretty much in the range of 995 to 999 for individual variables, because to get an aggregate loss in the portfolio, you needed a lot of things to move together, and those things would happen. Those things corresponded to the tail of the portfolio, but they were not the tails of individual factors. So the differences in the copulas, which were really in the extreme tail, didn't really matter. So for example, if you use student copula and you move the parameter of the student copula from, from 3 to 15, which is a big range, it didn't affect so much the aggregate value at risk of the portfolio. So I was kind of surprised, but when you looked at it, it makes sense, because each of the variables you have to have scenarios where each of the variables has a moderate but probable move, and then you put them together, you get an extreme move for the portfolio. So I wonder I agree with all the points you make, they're important statistical points, but depending on the level of risk you're interested in for the aggregate system, they might not be such a big issue, because you might not actually be looking at the tails of the joint tails so much if you look at something like 99.5% for the whole portfolio.
yes,
I didn't find such a big sensitivity.
unless if you go to 99, like if you look at 99.5% of the system, given that X is at 99.5%, you're really looking at exactly
Yeah,
this
you're looking at that,
joint
but
tail.
I wonder if that's really the right thing to look at, because you're really interested in the aggregate risk. So if I give you n variables, and you know these conditional quantiles, are you able to reconstruct any useful information about the tail of the aggregate risk loss? I mean, I'm saying maybe not. It's not obvious that you can.
Rama, this sounds as if it's a function of the dimensionality of the system, and if you have one institution contributing to the whole thing, you have a
Yeah.
bivariate setting, and you're very close to
Yeah, in the bivariate
this
setting,
thing.
clearly.
And you're
you need
looking
that.
at this whole
Yeah, if
portfolio.
you go
Yeah.
above 100, which is typically what you
I'm
do,
just conjecturing. It really depends on
yeah, it depends.
what quantities you're focusing on in the analysis.
Yeah.
But I understand your point.
Yeah, actually I don't have a clear answer on that.
Microdenstra and vanilla thing.
I'd just like to return to the question that was raised early on in your talk, that what you're working on are the observations, but there possibly are going to be even more extreme observations, and that's where extreme value theory comes in. Following the pioneering work of Ilyana Medova over in the corner there in operational risk, it's of course the very extreme thing. And there is another technique, it's computationally very expensive, but it works extremely well, which is hierarchical Bayesian modeling, even to quite high dimensions, and then Markov chain Monte Carlo estimation. So that answers the question that was raised for you, so to speak. I think this is a very interesting talk, though.
So thank you. The thing, we could look at the impact also having an extreme value distribution on the margins by you first transform to the normal 0-1 scale, you study your dependence, and then you go back to the original scale using extreme value distribution, and you'll see that it has a huge impact on the conditional distribution. Because conditional distributions are really a factor of like copula and marginal distributions. So you could have extreme value distributions for the margins.
We have two more questions. We still have some time.
I'm of course interested in the models where the dependence is changing over time. So that you can take out easily with the marginal, but the copula you assume to be time invariant. So another strategy is to fit a multivariate model and then examine the tail dependence and the residuals. So if you look at tail dependence in the residuals, then maybe we can use non-parametric approaches to looking for that rather than these faulty parameterization. I mean, basically what you're saying is that the parameterizations we think of are not very good.
You could do also a time-varying dependence. So there's some work on time-varying dependence, and all these copula have a parameter that you can make it time-varying.
Including your vines?
Yeah, they are, like, you can do it time-varying. Of course, the more you add, the more like flexibility you have, and probably model risk also when you fit it.
There was one more question. Let me take it before we get off.
A similar point to the time varying dependence. I like very much your warning that we should be careful with conditioning on equality and when to use quantum regressions and when not. So what we found in CoVAR is there was a huge difference between conditioning on equality and greater than equal, because if you condition on equality, you can compute the threshold when CoVAR starts to decrease, and it happens perversely when dependence increases a lot. So if you translate it to capital requirements, your conclusion would be, well, beyond this threshold, the more the banks depend on each other, the less capital they need.
Exactly.
And this trickles down to delta CoVAR and all related measures. So I think you're raising a very important point that we should understand what the properties as a function of dependence dependence is correlation for the normal, but it's not if we go beyond the normal. So it's a very important point.
And conditioning on less than equal, people haven't done that too much, because as soon as you condition to the inequality, then everything in the bivariate normal world becomes more complicated, because it's a skewed normal that you get instead of getting a normal. So normal condition on a normal is not anymore normal, it's skewed normal. But if you work in my setting where you have marginals and copulas, you also have a closed form expression for this quantized condition on the inequality. So it's not more difficult to estimate the conditioning on the inequality or conditioning on the equality, actually.
Okay. We are out of time.
Yeah.
Maybe just a quick one, but then...
Just a remark. I just want to continue with what Rob proposed on the non-parametric approach. In fact, you have given a very valid critique on the existing parametric families of copulas, because they don't capture asymmetry in the tail dependence, but in fact in the multivariate extreme value theory, which is not about, let's say, extreme value distribution in univariate tails, but in the bivariate tails, there is large literature on tail dependence function, which is essentially characterized by a spectral measure, and that allows all kind of asymmetry, and there's no parametric model, and there's valid unparametric statistics that can estimate that. And in that sense, you can get rid of this, let's say, constraints from parametric models that you must use symmetric tail dependence.
Yeah, you can include these bivet copulas coming from extreme value as a
Let me thank again Patrick and Carole.